goal of this tech talk is to give you a rough introduction to MicroPython. The goal is to not go into details, either technically or practically, let's say, but this is more to give you an idea of MicroPython. So I will start with the introduction, and then I will list some ports on which MicroPython can run. I will give you some resources. I will quickly give you some environment tools that you can use regarding MicroPython. Give you some use cases, advantages, disadvantages of MicroPython. And then I will give a quick internal architecture point of view and some performance talk on it. And then I will do some demo, but I will do the demo on the ESP32 microcontroller. So that's why I will introduce the ESP32 first. And then some further features that I will just go, let's say, list them without going into details, so that you know that they exist, but I won't go into details to avoid spending too much time. There is, I would say, one main alternative to MicroPython, so I will give a quick talk, but to be honest, I don't have any experience with this alternative. Yes. So maybe in the chat, I would be curious to know who has already used MicroPython. So if you can, in the chat, say if you use it as a professional use, as a personal use, or if you don't know anything about MicroPython. So yes, I would be curious about that. Okay. Okay, someone use it as personal, ESP32 first draft project. Okay. So the introduction. So that's interesting to know that MicroPython is actually a nice case, I would say, of a Kickstarter project. So it's a Kickstarter project that was launched by Damien George. So that's an Australian person, who is a physicist, and also, let's say, robotics enthusiast. So yes, and he is now maintaining full-time the MicroPython ecosystem, and he now lives in UK. So that Kickstarter was completely funded. Well, it was even more funded than the goal. I don't recall exactly the number. So it was completely funded in December 2013, and it was the goal of the Kickstarter campaign was to have the MicroPython, let's say, software side, and also hardware side, which is the PyBoard, which is the image that you can see on the bottom right. So that's a board that is based on the STM32F405 board, microcontroller. And then later on, he also funded, he also launched a campaign for the port to the ESP8266 microcontroller. So that was in 2016. So MicroPython is an implementation of Python 3 that contains a small subset of the Python standard library. And of course, it's optimized to run on microcontroller and in constrained environments. So it's packed with some features such as arbitrary precise integers, closures, list comprehensions, generators, exception handlings, and so on. And so that's to give you a rough idea, it can run on 256 kilobytes and 16 kilobytes of RAM. So the goal is to be as much as compatible with Python. In the demo, you will see that you feel like you are writing Python code. Yes, so that's the implementation is based on the Python 3.4. And then they take some features of the 3.5, 3.6, and so on. But the base is the 3.5. So it was written in C99, and it is in the license is MIT license. So for the ports, of course, it can run on the Pi board, the ESP32, the ESP8266, some Arduino boards, some the Raspberry Pi Pico, some Teensy boards, then ARM, Unix, and Windows. So you can see the full list on the website. That's where in the demo I will go further, but that's all the boards that you can run with the MicroPython. So as for the resources, you will see in the demo that I will use of course, the main website. So there are only two, I would say, two main things in this website: the download section, which I just shown you before, and of course the documentation. You have also a Discord channel, some discussions, wiki, and so on. That's the two main page that you will use on daily basis. Would be those two, I guess. Okay. Of course, there's the GitHub. You have there more ports. Well, those are the technical ports, I would say. So the ESP32 is the one that we will use in this demo. Of course, you can always use some MicroPython lists. So those are for the more the libraries and so on. So we will use some of them in the demo later on. In regard of the environment, one IDE would be if you want to work with IDEs. This ESP32 MPyGemma is one. Otherwise, you can directly put the Python file. You can push them with MPy. And there are probably more tools, but those are some of them. I will also show them in the demo. So in regard of the use cases, advantage and disadvantages, of course, basically for the use cases, you have a bunch of them, everything that you can do with a microcontroller, I would say. So you can do IoT, home automation, and also educational purposes, as it's very easy to get into microcontroller with MicroPython, as it's very easy to do some features development. The advantages, so of course it's easy to use. It's very fast to prototype. It's easy to find the library, import it, and use it. So libraries are also in MicroPython. So usually they are quite short in terms of lines of code. And also the REPL, so the read eval print loop that you can use. That you can use. Of course, disadvantages: the performance, the memory consumptions, and the limited low-level access. By that, I mean that you cannot do in MicroPython itself. You cannot do some features let's take an example. I was doing a project where I needed to do some deep sleep wake up from GPIO, and the way that it was integrated on the ESP32C3 port was not full, and so I needed more in-depth low-level. I needed a more in-depth wake up. So basically, the wake up was on all pin from low to high, something like that. And I did it something like just one pin or something like that. I don't recall exactly, but that was possible on the ESP32 with C usage, but not with MicroPython. So the internal architecture, so that's the code can come from three sources. So the REPL prompt from user scripts, and when you call the eval exec function from Python. Then after that, so I'm on the red cases here. I think I can even annotate. Yeah, I cannot find the button anymore. Oh, here we go. So that's the red boxes, and then here it's regular, I would say, compilation steps. So the lexer, the parser, the compiler, and then the compiler can output three different can output three different code, let's say, well, outputs. So the bytecode, which is run inside the virtual machine, that would be the default one. And then you can run also some native code and Viper code. So that's when you want to optimize the in regard of speed and memory consumption. And then, of course, it scores different built-in stuff. So all the yellow stuff here, and you can have also some external bindings. So this is from a very interesting talk that I've took here. So that's yes, I would recommend you if you want more information. So that's a talk regarding writing fast and efficient MicroPython. The next slides is also taken from this this talk. So yes, that's a 30-minute talk. So that's not too long to watch. Yes. Okay. So of course, at every steps, so the compiler steps, it will consume some memory, and then running the bytecode will also consume some memory. So of course you have like 2 times the memory consumptions while running the bytecode, because it needs first to compile, then run the bytecode. So let's take an example. So these are 4 lines just to blink an LED. So I will be so the question here is, what frequency do you think the LED will blink? And for that, let's take, so this code will run on the Pi board. So to give you an idea, that's a 160 megahertz microcontroller. Yes, so maybe in the chat you can give you an idea of what's the frequency of the LED blinking, if you have any idea, if you want to take a guess. Martin said 50 kilohertz. Any other guess? 200. Okay, then I have two guesses. One of them is very, very close to the reality. So I will give more suspense on this. So this is the full code. So we are running that for 200,000 times, but that doesn't matter. And then the line from 13 to 16 is just to measure the frequency. And so the answer is 57.93 kiloblinks. So sorry, it's not kilohertz, but of course it's kiloblinks. So the one blink, well, almost 58,000 blinks per second. So now we can try to have a better performance regarding this. So one way is to preload the methods. So that will avoid MicroPython to need to search in the global dictionary where is the LED object, and then where to call the on and off method. So you can load directly this on the on and off local variable of the function, and that will help in regards to performance. So that helps about, let's say, over 3 times. We blink 3 times faster. So that helps already. Another way, of course, is to unroll the loop. Of course, this makes the code less readable. Here it's just on off, so it's easy. But if you have a loop with tens or hundreds of lines, then it's not as readable as this. So of course, having performance as a cost of code readability, and yes, so you have to find the balance, of course. So here we also use the native outputs. So if I go back from here, we use the native instead of the bytecode. So that also helps. Okay, we can do even better. We can use the Viper, which is the third output of the compiler that I've talked about. And so here we can still in Python, so it's still Python code, but there we can write directly to the GPIO registers. And so again, we have quite a big improve here to around 13,000 kiloblinks per second. And then a last performance improvement is to use assembler, but of course writing assembler is more difficult than just writing led.on and led.off. But then here we have 27,359 kiloblinks per second. So basically the idea is that you can have performance improvements on Python, MicroPython code, of course, with the cost of easy development and code readability and so on. So that's a factor of 500 times faster code execution time. I mean. So yes, so basically the idea with MicroPython is that if you need performance, you can always improve the performance on some section of the code, but the main, I think there is no point of writing MicroPython and doing only assembler code, of course. So yes, so the idea is to just improve some points on your code, some sections of the code. So that's the summary of the talk that from the source that I was using. So that was a talk from Damien George, so the creator of Python, MicroPython. So basically the idea is to optimize at the end, and you can consider that Python code is roughly 100 times slower than C code. Of course, you can improve the performance on some sections of the code. You can always use some C modules, and you can also use some techniques such as using local variables instead of global variables, for example, and much more. Of course, the idea of this talk is not to give you an idea of the performance, well, to give you performance techniques and so on. So I don't want to spend too much time on this section. So now we can I can give you a quick demo. So for the demo, I will use ESP32, which is a quite known microcontroller. But for those who do not know it, it's a Wi-Fi and Bluetooth module. Well, Wi-Fi and Bluetooth capable module. So the ESP32 is just the BGN Wi-Fi. If some ESP32 has Wi-Fi 6, for example, Bluetooth also is here just the 4.2, but some other have better Bluetooth, more recent versions. It's a dual-core microcontroller. So I think this one is 240 megahertz. It has also ultra-low power processor, well, coprocessor that you can use. Of course, some GPIOs. There are two 8-bit tags. There are touch sensors, SPI interfaces, UART, and so on. So as I said, the ESP32, there are different series. So for example, the one that we will use is the let's say the classics. Oops, the classic series. And then there is the ESP32C series, which is more, let's say, cost effective series. So on this one you have Bluetooth 5. And then there is the H and the S and the P series, but I don't know much about those. I think the P is more high performance and so on. The S is for the secure, and the H it's more for the connectivity, I think. Yes. And the ESP8266, it's an older one. I don't recall when the first one was when this ESP8266 was on the market, but it's now recommended to upgrade it to ESP32C2, which is a quite close ESP variant of the ESP8266. So now I propose that we go to the demo. So for the demo, I will go from scratch. So download and install MicroPython on the ESP32. And then we can do some blink example. I will show you the web REPL. Then some MQTT client and some web server. So for the demo, I have here an ESP32. Let's go to the MicroPython. Let's do this here. I'm sorry, I will just move some windows around. So this ESP32 is this one. So that's the port, the binary that I will download for all ESP32 targets for the ESP32 series. I mean, if you have, for example, ESP32C3, then it's another target, another binary. I mean, okay, so on this page, you can even see the tools and the command lines that you need to flash the ESP32. So you can just erase the flash to be sure to come from scratch. Of course, it's not USB 0 on my board, it's ACM 0. So now my flash is erased on the ESP32, and I can flash the binary. Didn't I erase the 0 at the end? 1000, yes, that's good. Okay, so now I'm flashing the binary. So I took the version 22 because I'm used to this one, but the latest one is the 24, 1.24. But that should also work with the 124. Martin, I didn't have anything in my mind to win for the guess. I'm sorry.
Okay, there's always next time.
So now that I have flashed the MicroPython on the ESP32, I can just open Minicom. There's some chunks in the buffers, but if I reset, I have now MicroPython prompt, and I can just do stuff just as I would be doing on Python. I can import OS os.listdir. So we have also auto-completion. So now I just have in my file system just put.py. I can also import machine. In machine, I can, for example, I can do the deep sleep, for example, and let's deep sleep for 3 seconds. And now the microcontroller is not in deep sleep, so it just consumes a couple of microamps and then it restarts. Of course, you can set up in 1 or 2 lines wake up sources such as GPIO, and so on. So that's for the installation. Now we can maybe do a quick blink demo. So I can, of course, do here. So let's say from machine import spin. I will call it. I will also need some sleep for the blinking. So from time import sleep, and now I can do pin. So the LED is connected on pin 2. It's a pin that is an output, and now I can just do while true. So I turn it on, I sleep, let's say 0.5 seconds. I turn it off. And I sleep. Oops, I made a mistake in my sleep comment. Okay, let's start again. While true. And now you can see that it's blinking. So of course here it's in the REPL. So as soon as I reset the board, it will not. It will just go to the default. Nothing was written in memory. I mean, so as soon as I reset, it will not blink anymore. So to reset, you can either do Control D, well, Control C to kill the current code. So I can just break from the while loop. And if I do the Control D, it's just soft reboot. If I want to reboot from hardware, I can either do machine dot reset. Of course, I just reboot it, so I need to import. And now the board just resetted. Yes, so even if in hardware reboot, the LED seems to not be. I expected that the LED would be stopped, but no. So as I've said, we can also use an IDE. So I will quickly show you this. If that's does want something. Okay, demo effect, of course. Let's try one more time. Okay. So here I have connected to the ESP32. You can see the temperature, the uptime, RAM usage on the bottom left. You can directly connect to Wi-Fi from here on the board. So you can see all the networks that are available. You can also see the network states. So that's nice to just see the network states. You can use a REPL terminal as before. And you can also browse what's here. So if I want here to create, let's go to the code editor. Here, if I want to, I will just, whoops. So if I want here to have some code running, I can save it as main.py. And now, so now the main.py is on the file system. I can either run directly here, or if I reset, now the main.py runs. So even without the IDE plugged in, the main.py will run. Yes, so that's basically a nice way to start if you don't want to. I mean, for maybe educational purposes, it's a nice tool. Yes. Maybe I can show you now the web REPL. So that's basically just a wrapper that is accessible via the web. I will do that via Minicom, let's say. I will code it in live. So for that, I will need to connect to Wi-Fi. So import network. Yes. So to connect to Wi-Fi, I will need to have a network object. So I want it to be in stationary station mode. Now I can activate the Wi-Fi module. I can then connect to the Wi-Fi with the SSID. Nice password. Let's see if it's connected. So that's just a NIC is connected. So that's connected. I can import the web REPL and I can start it. So you need to give a password. Did I mistake? No password. Okay. 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 Demo effect again. Okay. I will do another way then. Let me this way. Okay, so I have to give you an idea of what I'm doing. So that's exactly the same code. So I'm importing the web REPL here, and then it should work. So here I've just used the MPy tool. Of course, I need to give the device, and then I'm putting my file here from my local disk to the target, and on the target I wanted to that the file is called main.py. I will open Minicom to see what's happening. Reset the device. Okay. So now the connection is made. It's connected to Wi-Fi. So if we have a look back to the code, you see that we can just print the ifconfig here. So print nic.ifconfig, and that's so of course it's DHCP here, and so you can see the IP address, netmask, gateway, and so on. And now I can go to the web REPL here. So I will copy the address and I will come from scratch here. So the address is WebSocket, the IP address, and the port is 8266. I can connect. The password is web REPL, and now I can see the exactly the same than what's here. I can stop, and then I can do whatever I want. If I want to again list here, I can see the two files, boot.py and main.py. If I want to read the files, I can. If I want to, I can send also a file from here. So yes. Okay, I'll try to go to the MQTT demo. Okay. Maybe question that I should have asked before is, do you see this well enough? I don't know, maybe I can do this to be better for you. So for the MQTT, well, actually I can do this. So for the MQTT, again, I will need to import the network. The idea of the MQTT example is to be able to turn on the LED from MQTT, and it would be easy also to just publish inside the MQTT topic. So we will do both. So for the MQTT, we will need again the pin for the LED. I will go more quickly because we've done that already for the network. So again, just this we've already seen, and I just print waiting for connections every half a second. If it's not connected yet, then I print the IP address. For that, I will need the machine. For the pin, I need the sleep method. Okay, so that's everything regarding this we've already seen. For the MQTT, we need the MQTT library. This, and then now it's everything regarding MQTT. So, okay. So we can create a client for the MQTT. We need to give a name to the client, let's say my ESP32, and then the IP of the broker. So that would be my local PC here, that's where I'm running an MQTT broker. I can then ask it to connect. Let's do a clean session. So that's we are sure that every time it connects, the session is clean. So maybe what we can do is set a callback. And because we need a callback to every message that we will receive, so we can subscribe to the topic, let's say LED. For the callback, we then need the method. So the callback will have two parameters: the topic and the message. The topic will be in byte array format. So let's it's easier to work with strings. So let's decode it. Decode. And we need to say that we need decode from UTF-8. Let's do the same for the message. So now we have a topic and a message. Let's print it. I will. And now we can say if the topic is LED, if the message is, let's say, on, then we can turn on the LED. If the message is off, then we turn it off. So that's it actually for the MQTT, except that we need to check that we receive the message every so often. So to do that, I'm going to use async.io. So we need to import it. Because I will do two loops, and instead of having one loop and doing different actions based on the time and so on, I will do two loops. So I will do, let's say, a slow loop. And a fast loop. A fast loop and slow loop. Okay, so now I will define what the slow loop and the fast loop are. And so the slow loop is just a while loop that does publishing to the, let's say, so we can publish to, let's say, a topic hello world. Hello world. Let's say the time. And we will do that every seconds. For the fast loop, so for the fast loop, we can check the message for the MQTT. Check message. And then we need to do that quite often. So let's do, I think, IO sleep 0. So here we're just sleeping 0, but it allows the async IO to know that it can, sorry, we need to do this way. So that async IO knows that it can change to allow the slow loop also to run. Yes, I think we can run this. So I will save. So MPy, and now I'm going to run the MQTT. Here we go. So that's now on the target, and I now also need the Do I need any library actually? Actually, I don't think. Yes, I need. I need the sync. No, I don't need the sync. It's already built in on the target. Yes. Okay, so I think it should be good. So we can minicom on the target. Reset. I think is not defined. I think you.
There is a typo.
Oh yes, indeed. Thank you. So IP address is still the same. So now I can go on my MQTT. So I use MQTT Explorer to see my MQTT broker. And so here I see that in the Hello World topic, it's increasing every second. And I have this topic here that I can publish to. So I can publish on, and it should just turn on. I can publish off, and it turns off. So that's working. Just have one more demo I will do quickly. So that's the demo where I have a web server running on the ESP32. So because runtime is running out, I will just do copy paste from my cheat sheet. So I will import microdot, which is a library that is basically just like a fast API, if you know fast API. So what I want is that I want to run the application. So I want to run the microdot application. Just like in Fast API, I can use decorator on my functions. Here I have a decorator that says that as soon as I have a HTTP request on the slash on the root, then I need to send the file index.html. Of course, I need also to have the app started. So for that, I can run another loop, which would be the app start server. Actually, it should not even be a no. Yes, it needs to be a loop. And so this loop, I will just add it to the async.io thing here. So basically, here I just gather some loops that are run in parallel. So this loop, and this loop are run in parallel. Do I need anything else? I don't think so. Okay, I will save. I will send it to the ESP32. And then I will also send some other files. So I need to send the index. I need to send the index files to which this is the HTML that should be served. I also need to send the microdot async.io. which is the library. And so that's one part of the library, and this is the other part. I think that's it. Yes. Okay. Back to Minicom. Reset. Why did it wrong? Oh, what's? I don't know why it got there. Oops. Oh, I don't know what happens if I abort this, so I will just do it again. So this one. Okay, back to Minicom. Okay. And I should be able to. So on the targets 192. What did I miss? Let me check something.
Maybe because of the HTTPS in the URL.
It seems like no. I still have this. I don't know why. Don't know if I should have complained before though. Check. I will push again. It should have complained. So no. 04. Let's make sure that it's not if I do curl. No. Okay. I will try to figure that out after the tech talk, and I will keep you updated of why it was not working. Because yes, I don't see it. I don't understand why. Okay. Well, sorry for this. Sorry for this. Yes, everything should be good. Okay. Yes, sorry for this. I will keep you updated. Try to figure that out. So quickly, those are the further features that you can see. So you can do OTA, so over the air update of MicroPython. That's possible. I don't want to, as time is running out, I will not talk too much about this. You can extend MicroPython in C. So you can write some C that is compiled to the MicroPython binary. And then you can run those C section of code directly from MicroPython. In the doc of MicroPython, if you are curious, you can see the differences between MicroPython and the big Python, let's say. So that's interesting to read. As you've seen in the demo, I've used some MPy files. So there are the bytecode of the bytecode. So there it's the equivalent of the .pyc file on the big Python. So it allows you to reduce the RAM usage, which is quite useful if your application is quite big, or if you are using big libraries. That's why the microdot library was with the MPy files. Also, the PyCon Australia, PyCon US YouTube channels have quite interesting call on MicroPython. So if you want to read more, to watch more, and then you can view some of those. One of the alternatives, as I said, of well, the only one actually I know, which is very similar to MicroPython, is CircuitPython. It's from Adafruit. It's actually a fork from MicroPython in 2017. And the differences are not huge in my mind, at least. So that's what they say in terms of differences with the MicroPython. To me, the main idea is that it's easier, for example, well, easier in terms, for example, of education, because the error messages are translated into a couple of languages. The other, I cannot comment on the other differences. Yes, that's it. This tech talk was interesting that you've learned on MicroPython. I don't know if you have any questions. If not, then we can conclude this tech talk. Thank you a lot, and see you later.
Thank you.
You're welcome.
Thanks,
you.
Benoit.
Bye.
Thanks, Benoit. See you.
Shabbat.